When dealing with overcurrent protection for step-up transformers, neither National Electrical Code Table 450.3 nor 450.3b is directly applicable because they don't account for step-up transformer configurations. Instead, focus on Section 450.4, which addresses transformers in general. Specifically, Section 450.4 covers overcurrent protection, stating that transformers must be protected against overcurrent as described in 450.3a or b, with some exceptions outlined in 450.4a on through 450.4fr. However, the relevant section for your particular application, step-up transformers, is 450.4a3. This section explicitly states that for step-up transformers, the input or supply side should be considered the primary and protected according to 450.3a. Diving into section 450.3a, it says that transformers must be protected against overcurrent using one of two methods: firstly, primary-only protection, or secondly, primary and secondary protection. Primary-only protection means the supply side is protected by a single overcurrent device rated or set to limit the current to a value that won't damage the transformer or under any condition of secondary loading. The rating or setting of this primary overcurrent device should be based on two considerations: firstly, the rated primary current of the transformer, and secondly, the transformer's overload capability, if any. Given the customer's existing setup of a 240 volts delta system, a delta-delta transformer configuration is the most suitable choice. This allows you to leverage Section 240.4f for secondary conductor protection. Section 240.4f outlines conductor protection, stating that conductors must be protected against overcurrent in accordance with 240.3 or the provisions within that section. Specifically, Section 240.4 phone pertains to feeders, allowing branch circuit and feeder conductors to be protected by an overcurrent device on the supply side, but only if certain conditions are met. All of the following. Firstly, the conductors must be protected by the overcurrent device within their ampacity. Secondly, the overcurrent device must be rated no greater than 125% of the circuit's ampacity. Thirdly, the overcurrent device must be of the inverse time type. A few important considerations to keep in mind. Firstly, although a 4160 volts transfer switch may initially seem more expensive than a 240 volts transfer switch, it simplifies the overall system design and eliminates the need for an additional step-up transformer. Secondly, ensure the 480 volts generator includes a neutral terminal that is solidly grounded at the generator itself. Thirdly, the transformer should be sized appropriately to handle the anticipated load. Finally, the transfer switch must be rated for the full load current and the available fault current. In summary, sizing the overcurrent protection involves determining the primary current of the 480 volts to 4160 volts transformer. For example, if you have a 300 kV amps transformer stepping up from 480 volts to 4160 volts, you'll need to calculate the primary and secondary currents. The primary current is calculated by dividing the kilovolt amps by the primary voltage and multiplying by 1.732 for a three-phase system, resulting in approximately 361 amps. The secondary current is calculated by dividing the kilovolt amps by the secondary voltage and multiplying by 1.732, resulting in approximately 41.7 amps. Using Section 450.3a, you'll use a primary side overcurrent device size no more than 125% of the transformer's rated primary current, assuming no specific transformer overload capabilities are provided. In this case, 125% of 361 amps is approximately 451.25 amps. Therefore, a 450 amps overcurrent protection device would be suitable. Remember, this value should not exceed what is permitted by the transformer specifications or relevant standards. When selecting conductors, you'll refer to NEC Table 310.16 or other appropriate tables to determine the ampacity of the conductors based on the termination temperature ratings of the equipment. Make sure the conductors are rated to handle at least 125% of the continuous load as required by the NEC. For a delta-delta transformer configuration, phase-to-phase voltage on both the primary and secondary sides will be considered. The delta connection on the primary side means no neutral is present and the overcurrent protection is provided for each of the three phases. The same is true for the secondary side in a delta-delta configuration. When applying section 240.4F for secondary conductor protection, ensure that the conductors are protected within their ampacity. The overcurrent device is rated no greater than 125% of the circuit's ampacity, and the overcurrent device is of the inverse time type. The inverse time characteristic ensures that the circuit breaker or fuse will trip faster with higher levels of overcurrent. Also, the 480 volts generator should have its neutral bonded to ground at the generator itself. This is especially critical when dealing with the 480 volt system derived from the generator. Grounding the neutral provides a reference point for the voltage and helps protect against overvoltages and fault conditions. Be aware that if the 4160 volts system is ungrounded, there may be additional considerations for grounding and ground fault protection. Furthermore, the selected transfer switch should be rated for the full load current of the system, meaning it should handle the maximum current that the system is expected to draw under normal operating conditions. It should also be rated for the available fault current at the point of installation. The fault current is the amount of current that would flow during a short circuit condition. Choosing a transfer switch with an adequate fault current rating ensures it can safely interrupt the fault current without being damaged. Coordinating the overcurrent protective devices is crucial for selective tripping. This means that the overcurrent device closest to the fault should trip first, minimizing the impact on the rest of the system. This coordination prevents unnecessary outages and helps isolate the fault quickly. When dealing with high voltage systems like 4160 volts, safety is paramount. Ensure that all work is performed by qualified personnel who are trained and experienced in working with high voltage equipment. Always follow proper lockout/tagout procedures to de-energize the equipment before working on it. Use appropriate personal protective equipment (PPE) such as insulated gloves, sleeves, and face shields. Before putting the system into service, perform thorough testing and commissioning to verify that everything is working as intended. Testing should include voltage and current measurements, insulation resistance tests, and functional tests of the transfer switch. Be aware of the specific requirements of the local utility company. They may have regulations regarding the connection of generators to their grid, including requirements for protective relaying, synchronizing, and isolation. The NEC provides minimum safety standards, and it's essential to consult with a qualified electrical engineer and adhere to all applicable codes and standards to ensure safe and reliable installation. In addition, carefully consider the generator's fuel supply and storage. Ensure that the fuel supply is adequate to run the generator for the expected duration of an outage. Also, ensure that the fuel storage is in compliance with all applicable regulations and that proper safety measures are in place to prevent spills or leaks. Regularly inspect and maintain the generator and transfer switch to ensure they are in good working condition. This includes checking the oil level, coolant level, and battery condition, as well as inspecting the wiring and connections. Keep detailed records of all inspections, maintenance, and repairs. The generator location needs to be considered. Ensure there is adequate ventilation for the generator to prevent overheating. The generator should also be protected from the elements such as rain and snow. If the generator is located indoors, ensure that it is properly ventilated to prevent the buildup of exhaust fumes. Also, consider the noise level of the generator. If the generator is located near residential areas, noise mitigation measures may be necessary. Consider a comprehensive monitoring system to track the generator's performance and detect any potential problems. This system can monitor parameters such as voltage, current frequency, and fuel level. It can also provide alerts and notifications in case of a fault or abnormal condition. For example, you may want to install a system that sends an email or text message to maintenance personnel if the generator's fuel level drops below a certain threshold. Remember that the specific requirements for overcurrent protection, grounding, transfer switches, and other aspects of the installation will vary depending on the size and configuration of the system, as well as the applicable codes and standards. Consult with qualified professionals and conduct a thorough engineering analysis to ensure that the installation is safe, reliable, and in compliance with all applicable requirements. Ensure all equipment used is properly listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories Incorporated or Intertech. This listing provides assurance that the equipment has been tested and meets applicable safety standards. Also, be aware of any energy efficiency requirements that may apply to the generator and transformer. Consider using energy-efficient equipment to reduce energy consumption and lower operating costs. For example, you may want to consider using a premium efficiency transformer that meets or exceeds the minimum efficiency requirements of the Department of Energy. Also, consider the environmental impact of the generator. Ensure that the generator complies with all applicable environmental regulations, such as those related to air emissions and noise levels. You may want to consider using a generator that is certified to meet specific emission standards. Also, consider the disposal of used oil, coolant, and other fluids from the generator. Ensure that these fluids are disposed of properly in accordance with all applicable regulations. Make sure that the generator and transfer switch are properly integrated with the building's fire alarm system. In the event of a fire, the fire alarm system should automatically shut down the generator and transfer power to the normal utility source. Also, consider the security of the generator and transfer switch. Ensure that they are protected from unauthorized access to prevent vandalism or theft. For example, you may want to install a fence around the generator and transfer switch and equip them with alarms and security cameras. Moreover, confirm that the generator and transfer switch are accessible for maintenance and repairs. Ensure that there is adequate space around the equipment for technicians to perform their work safely and efficiently. Also, consider the availability of spare parts for the generator and transfer switch. Ensure that spare parts are readily available to minimize downtime in case of failure. In addition to all these electrical considerations, take the time to consider the structural requirements of supporting the generator and transfer switch. Ensure that the building structure can support the weight of the equipment. Also, ensure that the equipment is properly anchored to prevent it from being damaged by wind or seismic activity. Finally, don't forget the importance of training. Ensure that all personnel who will be operating or maintaining the generator and transfer switch are properly trained. This training should cover topics such as safe operating procedures, troubleshooting, and maintenance.